Bonjour à tous. Okay, so in this next video in the fundamental toolkit of chemistry, we have chemical bonding. So chemical bonding tells us everything that has to do with all of the molecules and structures that we know of. So there are three main types of bonding: covalent bonding, metallic bonding, and ionic bonding. So covalent bonding forms the bulk of the syllabus because well, there are so much more things that you learn now as opposed to what you have learned previously. So let's cover covalent bonding first. So covalent bonding is the electrostatic forces of attraction between the positively charged nuclei. It's nuclei because you form a covalent bond between two atoms, right? So positively charged nuclei and the shared pair of electrons. So how this occurs is when there is orbital overlap. So if you recall, in atomic structure, you have your sp and d orbitals, right? So there are two main types of overlap. One is known as sigma overlap or sigma bond, which is a head-on overlap, right? Which occurs between the SS, SP, and PP. So as long as there is a head-on overlap, it's a sigma bond, and it is always the first type of bond that is formed. Next, we have the pi bonding. So pi bonding is a side-on overlap, which is formed only between P and P. So sigma bonding is more efficient because you have a head-on collision as opposed to like a side-on overlap, right? So in essence, the sigma bond is stronger. Okay, on top of this, the orbitals can undergo this thing called hybridization to achieve a lower energy. As we mentioned previously, a stable configuration is always one that has a lower energy level. So that's why we always want to, as long as there's a way to form a lower energy, we will do it. Okay, so orbitals can hybridize to do that. And after hybridization, you will get either sp3 hybridized through a tetrahedral structure, sp2 hybridized through trigonal planar, and it's a trigonal planar geometry, and sp hybridized, which is a linear geometry. So this just means that sp3 just means that you have a s orbital hybridized with 3p orbitals. sp2 means 1s and 2p, and sp means 1s and 1p. Okay, what these geometrical shapes mean, I will look next. Okay, so this geometry is determined by something known as valence shell electron pair repulsion theory, VSEPR. VSEPR has two main rules. One is that the electron groups around the central atom, remember it's always with respect to the central atom, they will arrange themselves as far apart as possible to minimize mutual repulsion. So this is like social distancing, okay? And the strength of repulsion will decrease from lone pair to lone pair bond pair and bond pair. So I'm not going to go through everything here because it's just a list that you need to remember. But during the exam, if you somehow forget stuff, you can always just grab 4 pens. So let's just say I have like tetrahedral, right? So if you have like tetrahedral, so this tetrahedral, right, you have 4 things. And then the next, if you want to go from like, if you have one lone pair now, you just remove one. And then now you have trigonal pyramidal. After that, you just remove another one, and then you have bent. So that's how you can sort of like cheat during the exam using what you have, right? Nobody says you cannot bring a pen in, right? Okay, I'm going to go through this. Let's move on. So some kind of questions that they'll ask you is, right, so we have like the values here, right? 109.5, 107. So how would it differ if we have, say, like a different structure? So the bond angle can change depending on the central atom, right? So you need to observe the differences in the central atom and not anything else, okay? So if something is more electronegative, you pull the electrons closer towards you. So when you pull the electrons closer towards you, then the bond angle will increase because there will be larger repulsion, right? And if you have more lone pairs, the bond angle will also increase. Why? Because the lone pair repulsion will occur. Okay, then we look at 2 other types of bonding. One is called the expansion of octet. Expansion of octet only occurs from period 3 onwards. So that means if you look at a periodic table, it is the period that contains like phosphorus and then everything below it. Not the group, the period, okay? So that row. And the reason behind this is because now from period 3 onwards, you are in the principal shell number 3. And principal shell number 3 has 3d orbitals. And 3d orbitals allow you to expand octet because now you can keep the electrons in there. Okay, the next type is dative bonding. Dative bonding is it's like kind of like the last resort because if you think about it, you form a bond by sharing, right? But in dative bonding, it's like sharing, but you give 2 of the electrons to the other atom. So instead of sharing, you give completely. So why is that favorable when you can share, right? So the reason is because you still need to obtain your octet configuration, but you can't unless you give it to someone else. So dative bonding is usually for stuff that cannot expand octet and have a lone pair of electrons. So then there will be complete donation in the form of a sharing. Okay, so it's like sharing but donating at the same time. Okay, next we look at polarity. So polarity is an important concept when we look at physical properties, right? So polar molecules have this thing known as a permanent net dipole moment, which just means like a permanent overall charge kind of thing. That okay, it's an analogy, but yeah. So I came up with this flow chart over here that you can use. Basically, you just follow the instructions and it will tell you whether it's polar or non-polar. Okay, this summary sheet is quite long because I included a lot of graphics, right? So this is the only one that is 2 pages. Okay, so next we look at the type of structures that come with covalent bonds. So there are simple covalent structures, which are things like your nitrogen molecules or water molecules, right? So between simple covalent structures, we will compare the intermolecular forces of attraction because when we look at them, we don't want to break the bond in between them because if you break the bonds in between them, they don't exist as a molecule anymore. So there are 3 main types of intermolecular forces of attraction. The weakest of them all is dispersion forces, but dispersion forces are present in all molecules. And it's because of this thing known as an instantaneous dipole. So if you look at the graphic over here, you can see that sometimes molecules can always stretch or bend or whatever, right? So when they do that stretching, there is a temporary instantaneous dipole. And when you now have a separation of charges, you can sort of polarize another molecule. And then in that instance, you have a temporary dipole moment. And you induce another temporary dipole moment. So this is called instantaneous dipole, induced dipole. That's why it's ID. Or you can just write dispersion forces. Next, we have permanent dipoles, which are only present in polar molecules. So based on the chart that we looked before, if you use, of course, you should figure out what are polar molecules, right? So polar molecules it's the same logic, just that instead of an instantaneous dipole, is a permanent dipole. So permanent dipoles can interact with other things, and then you get permanent dipoles and permanent dipoles will interact with each other, and then you get permanent dipole interaction, which is PD-PD. Next is hydrogen bonding. Hydrogen bonding is the strongest of 3 and only occurs when these 2 conditions are met. First, you have a hydrogen that is directly bonded to fluorine, oxygen, or nitrogen. And if another fluorine, oxygen, and nitrogen contains lone pairs of electrons. Okay, so in this figure over here, we have a carboxylic acid molecule, something like ethanoic acid, right? So as you can see, the oxygen, the double bonded oxygen here it's not connected to O, right? But it can still undergo hydrogen bonding because it has a lone pair of electrons, and it will form hydrogen bonding with the hydrogen that is connected with the oxygen. So just remember that if you have hydrogen bonding, so it's like if you draw a Venn diagram, right? If you draw a Venn diagram, if you draw a Venn diagram, I think I'm drawing. If you draw a Venn diagram, if you have hydrogen bonding, you have all of them. If you have PD-PD, you have PD-PD and dispersion forces. And then if you have dispersion forces, you only have dispersion forces. So yeah. Okay, so let's move on to next, giant covalent structures. So giant covalent structures are things that you start to look at the covalent bonds because you can break the covalent bonds. right? Because it's a giant structure, and then it has a regular arrangement, right? So there are three main covalent structures in your syllabus. One is silicon dioxide, SiO2, which is like sand, glass, right? And then there's diamond and graphite. So silicon dioxide and diamond have a tetrahedral arrangement and only have strong covalent bonding, okay? But graphite is a bit different. They are hexagonal sheets with dispersion forces in between those sheets. So this dispersion force is the weak interaction that allows it to like act as a lubricant or allow you to use your pencil and right. So one other important thing is that in graphite, the fourth electron is delocalized, because if you look at each of these structures, the carbon is really only bonded to three of them. Okay, just focus on this carbon over here. Focus on this carbon over here, because it's a regular arrangement, so I didn't draw all of them. But if you just focus on this carbon over here, you can see that it's connected to only three of them. But you know carbon can have 4 bonds, so the fourth electron is not there. So it's delocalized in the system. Okay, next let's look at metallic bonding. Metallic bonding is the electrostatic force of attraction between the metal cation and the sea of delocalized electrons. This electron sea model is the one that we are using in this syllabus to explain most of the properties. So metallic bonding very simply forms giant metallic structures, right? And the strength of the bonding is determined by the charge density, which is the charge over radius ratio. So if you compare like Mg2 plus to Fe3 plus, then you can look at the charge. Charge is quite simple, right? Fe3 plus is 3 plus, and Mg2 plus is 2 plus. The radius you can look at page 52 and 53 of your 51 and 52, I think, of your data booklet, and then you can look at the values and compare the ratio. So a larger charge density has a higher strength. Next, we look at ionic bonding. Ionic bonding is the electrostatic forces of attraction between oppositely charged ions. In the exam, if they ask you for ionic bonding, please specify what the oppositely charged ions are. So if it's like NaCl, then say it's between Na plus and Cl minus. So very naturally, they form giant ionic lattice structures, very simple to remember. And the strength is determined by this thing known as lattice energy. So lattice energy is proportional to this formula here, the product of the charges over the sum of the radius. So the charges are very simple, you can tell from the ions itself, and the radius is taken from like pages 51 and 52 of the data booklet. So why we need to know all of this bonding is also so that we can predict physical properties. And the three main physical properties that you need to be able to answer are electrical conductivity, melting point and boiling point, as well as solubility. So in electrical conductivity, we always want to identify what the mobile charge carriers are. Melting point and boiling point will be the relative strength of the bonding, or in the case of simple covalent structures, we look at the intermolecular forces of attraction. For solubility, we look at the overall interaction. So between the solute and the solvent itself, so that's one group. Another group is the solute, and the other group is the solvent. So as long as the interaction between the solute and the solvent is stronger than the individual groups itself, then the thing is soluble. So I have put up a table here that you can read on your own, because there's not much to explain about this. But this table sort of summarizes everything that I've said earlier. So it's a summary of a summary. And I think it can be quite useful for you if you want to come up with some form of format or template when you are trying to answer your questions. So always remember to state the structure and the bonding first, because if you answer every part of the question, every other part of the question wrongly, like you predict wrongly or something, at least if you have the structure and bonding, you still get half the marks. Okay, some marks, I mean, maybe not half, but some marks. So if you like this cheat sheet, you can go and get it on the coffee shop, or consider signing up as a member on the coffee shop as well. And you can always support by just donating if you don't want to sign up for a membership. Okay, bye-bye. See you in another summary.